Good. So this was information gain. Now a second measure that is very often employed is G-squared statistics. And G-squared statistics somehow measures the independence of D from the class variable. So before we had some kind of purity measure. Now we want to measure the dependency, or the other way around, the independency of the feature distribution from the class label. Yeah? And we can do that with a so-called contingency table. So we divide the data based on a split value, again, like we did that before, S for example, or based on some discrete values. So here is an example. We split the data by looking at if people like science fiction movies or do not like science fiction movies, and our class variable is playing chess or not. Yeah, so here is the contingency table. So people that like science fiction are in total 450 in the training set, and 250 of them play chess and 200 of them do not play chess. And out of the people that do not like science fiction, 50 play chess and 1,000 not play chess. A total of 1,050 do not like science fiction. And here are the sums below. Yeah. So now you want to try to see how independent those splits, or this split here, is from the split according to the class attribute. Yeah? So the class attribute, of course, also defines a split, and this one here is also a split, and now you want to see how independent those two different splits are actually. And for that purpose, you can compute the chi-square test with this formula actually, and the most important thing is that this one here. So Ij is the observed frequency of value j in class I. Yeah, so for example, the observed frequency of value do not like science fiction in class chess, which is 50. Yeah, and this Eij is not the observed one, but the expected frequency of value j in class I. So what is that here? Well, if you see play chess and not play chess, what is the frequency here? So you have a relationship of 20% to 80%. 20% of all the people in the training data set play chess, and 80% not play chess, do not play chess. So the expected value for not liking science fiction would again be 20%, 80%. So 20% of the 1,050 should play chess, or you would expect that 20% of those guys here play chess, and 80% of those guys do not play chess. Yeah, and 20% of those guys here that do not like science fiction should play chess again. 20% of that is 90. Yeah, and the remaining guys, 360, that do not like science fiction should not play chess. Yeah? So those are the expected values, and now you can compare those two things, the observed values and the expected values, and you see if this one here is more or less the same, the whole thing comes down to 0 actually. So in that case, if the dependence is good, yeah, if this one is small, it's good, yeah, because if it follows the class distribution, that means that this particular split is good to predict the class value. So you want to have a small value here, meaning that O and E are more or less similar. Yeah, the more similar the observed values and the expected values are, the more dependent is the feature and the class variable, and that is perfect because you want to have a feature that has a high correlation, a high dependence with respect to the class variable. So smaller values of the chi-squared distribution of this chi-squared test are obviously better. So here's an example. We compute the chi-squared values for the tables we had before. The numbers in the parentheses are the expected counts. Okay, so we talked about that before. We have a class distribution here in summary of 20% and 80%. So 20% of all the guys, of all the persons in our training set, which are 1,500, do not play chess. 300 of 1,050 are 20%, and 1,200 are 80%. So the expected values for playing chess in the not like science fiction fraction of 1,050 people would be 50. And the not play chess fraction in the not like science fiction fraction should be 1,000. Completely wrong. I'm sorry. 20% of those here are of course 210, and 80% of those ones here are of course 840. Sorry. That are of course the expected values here, and the same holds true here. So 20% of 450 should play chess, so 90 should play chess, and 400, and out of those 450, 80%, so 360, should not play chess. And now you can compare those. So here is the number crunching, and you see here that the chi-square of this science fiction like or not like attribute is 500 something. Well, of course the sheer number doesn't say anything to you or tell you anything, but now you can compare different attributes, and of course you will take those that have the smaller values. So you will take the k attributes that have the smallest g-square values in that case. Okay, so next one is mutual information. So in general, the mutual information also tries to measure the relationship, but now in terms of uncertainty. So if you know anything, so you take two variables, x and y, two features, x and y, and you want to measure how much does it mean to you if you know anything about x. How much do you also know about y in that case? So how much knowing about one of these variables, one of these features, reduces the uncertainty about the others. In other words, if you know something about x, how much can you derive from this knowledge about y? So in our case, it measures how much the information of a feature contributes to making the correct classification decision. So x is the feature and y is the class label, and you now want to know if you know something about x, how much does that contribute in knowing about y? So how much does that contribute in making the right decision actually? And the mutual information is based on probability distributions. You take the probability distribution, the marginal probability distributions of the two features here. So the feature you want to evaluate and the class label, and you also take the joint probability distribution of those two features. The feature you want to evaluate and the class label once again. In the discrete case, it's just the log likelihoods and the sum of the log likelihoods here. And in the continuous case, it's a little bit more tricky because you need to compute the integral, but that's in both cases not a big deal actually. You do not need to really understand this one here, but you need to understand what it's actually computing. So, or what does it mean? So the interpretation here is, if those two features are statistically independent, what does it mean? Well, then you can statistically independent means that the joint distribution is the product of the individual distributions. So in that case, this one here, the fraction, gets 1 because the denominator and the numerator are the same. So you have log 1, and log 1 is 0. So the whole thing in that case comes down to 0. So in other words, if you know x and that does not reveal anything about y, then the whole thing is 0. So mutual information should again be maximized. So higher values are better in that case. Yeah. So that was again the wrong direction. So a short discussion, summarizing discussion on forward selection. So the advantages are it's extremely efficient. It just compares each feature separately to the class label and just takes the best k. Yeah. So this is a linear effort in the number of dimensions, depending of course on the evaluation measure. But that's much better than just testing all possible k subsets of n, which is n over k actually. Yeah? And it also works typically already quite good for small sample sizes, because all those measures here are one-dimensional measures and quite simple, not too simple, but quite simple models. So you need not too many sample sizes in order to get robust estimates for all of those things. Yeah? So that is definitely an advantage. Limitation, of course, is the independence assumption. So features must display a direct correlation to the class. Yeah. There is no, so you don't consider any correlations among features. So in case of correlated features, you will always select the features having the strongest direct correlation to the class label. Yeah. Even if there may be some features that are not so strongly correlated to the individually to the class label, but together they are more strongly correlated than the others. Yeah. So that is the downside, but on the other hand, you get a really efficient feature selection preprocessing.